Now that we've looked at those three interpretations of probability and saw how we could use the different interpretations to assign probability to simple events under specific circumstances, we want to turn our attention to the decision procedure, the means by which we go from those probability assignments to simple events to computing the probabilities for complex events of which they are constituents. So we're going to have 5 basic rules. We're going to have a restricted conjunction rule, a general conjunction rule, a restricted disjunction rule, a general disjunction rule, and then a negation rule. In addition to these 5 basic rules for computing probability of more complex events from the probability of simple events, we're also going to talk about and introduce a very simple version of Bayes' theorem, which will allow us to update our probabilities in light of new information. And then we'll finish off the probability theory lecture by talking about translation heuristics again. Specifically, how do we go from a description of an event or a problem or the event or a problem in the world to translating it into probability theory, understanding its structure so that we can identify how to break that problem down and apply the rules in appropriate order. Now, as I say, there is no mechanical procedure for this. It's not an effective decision procedure, but I do give you a flow chart that gives you some structure about how to go through and break down problems so that you can figure out what their structure is, how to apply individual rules and sequence them so that you can get the correct answer. So this is the mathematician Jacob Bernoulli. He's very influential in the development of the probability calculus, which is the common name for our decision procedure. And we have these 3 different approaches to assigning probability to these single simple events. Our decision procedure now allows us to calculate or prove the probability of more complex events from the probability of those constitutive simple events. And they have these 5 basic rules that we're going to go through right now. Our first rule is the restricted conjunction rule. So the restricted conjunction rule applies whenever that condition holds, namely that the events are independent of each other. So one's happening doesn't affect the likelihood of another one happening. So if we know that the events aren't causally or otherwise connected, we can calculate the odds of their both occurring using the restricted conjunction rule, which tells us that the probability of A and B equals the probability of A times the probability of B. So let's see how we'd use this rule in an example. Suppose we want to compute the probability of Bill getting an A and Jill getting an A in a class without a curve, so that their grades don't affect each other, they're independent events. Well, we'll start off by estimating the probability for those constitutive simple events, Bill getting an A and Jill getting an A. Then we'll enter those values into our restricted conjunction formula, and we'll perform the calculation to get our result. So let's see how that would go. Let's say that we, look at their history of grades in classes on their transcript, and we use that to assign probabilities to the simple events based on the frequency interpretation. So we estimate that Bill gets an A about 0.75% of the time, or 75% of the time. The probability is 0.75. Jill gets A's about 90% of the time, or a probability of 0.9, 9 out of 10. Now we plug those values into our formula so that we multiply 0.75 times 0.9, and we perform that calculation, and we get the probability that both Bill and Jill will get an A in this class that doesn't have a curve. And that probability comes out to be 0.675. And this is something that you ought to know. Whenever we have conjunctions, the probability of the conjunct will never be greater than the probability of the least likely conjunct. So conjunctions always going to be no higher than the least probable conjunct. So when you're doing your calculations, if you get a number that's higher than one of the conjuncts, then you know that you likely have gotten a problem in your calculations. Now you might think to yourself, well, why are we multiplying for conjunction? And you can see how and why we multiply just by looking at a simple case. So say we want to calculate the odds of rolling a 1 on the first roll of a die and a 3 on the second roll of a die. Now each roll introduces 6 possible outcomes. And so there are 36 possible ways our world could go, 36 different combinations of values on our rolls. So that first roll gives us 6 possibilities. That second roll gives us 6 possibilities for each of the original 6 possibilities. And that is what gives us our 36 possible combinations. And knowing that, we can now see why it is that we multiply. When we multiply one's probabilities, we calculate the total number of possibilities by multiplying the denominators. So in this case, 6 for the first roll, 6 for the second, 36 possible combinations. Likewise, one calculates the total number of favorable outcomes by multiplying the numerators. In this case, 1 times 1 is 1. And so by multiplying our probabilities here, we determine how many combined possible outcomes of these two events we have and how many of those combinations actually get us the favorable outcome. What about a more general conjunction rule? Suppose it's not the case that that independence rule or that independence restriction on our restricted conjunction rule applies. Suppose that they are somehow connected to each other. Well, then we want to adopt this general conjunction rule. And it tells us that the probability of A and B equals the probability of A times the probability of B given that A is true. So it takes their connectedness into account. And you can symbolize B given A this way. Sometimes it's symbolized this way as well. So let's see how that would work in an example problem. So suppose we want to compute the probability of Bill getting the last cookie in the cookie jar and Jill getting the last cookie if Bill's already eaten it. So they are not independent of each other. Whoever gets that cookie makes it impossible for the other person to get that cookie. So step 1, we'll estimate our simples. Step 2, we'll enter our values. And step 3, we'll perform our calculation. So in this case, let's suppose that we use subjective probability. Based on our experiences, how likely is it that Bill and Jill are going to be victorious in the cookie competition? So our probability that Bill is going to be victorious is 0.72. Now, our probability that Jill is going to also get that cookie, given that Bill already got it, is going to be 0. So we're assuming there are no Sesame Street cut the cookie in half alternatives. One gets all of it, the other gets nothing. Now we enter those values in, and we have 0.72 times 0. We perform our calculation, and so the probability of this outcome, where both of them get the cookie when only one of them can, is 0. In the next module, we'll turn our attention to the disjunction rules.